Hello everyone. For this tutorial video, I'd like to show the segment of a cone, as well as show concretely how it is similar to the segment of a cylinder. The first way to obtain the segment of a cone is exactly like the first way to obtain the segment of a cylinder, which is to imagine the segment as simply a circle with height times 1/3. So we would use this formula but multiply height divided by 3 by the segment of a circle instead of a full circle in terms of the area in order to figure out the volume of the segment. To figure out the surface area, we would simply add the portion of the fan that constitutes the height, which would be the arc length of the quarter circle that constitutes a full cone, reduced instead to the arc length of the segment. And we would add the part of the ellipse that constitutes the non-curved face to get the total surface area. However, the second method is also similar to the second method of the cylinder, which is dissecting it in a way that is perpendicular to dissecting it at the top, i.e., dissecting it along the height so that you cut the height short, which is still called truncating it. However, truncating using this method is much more interesting for cones than for cylinders, owing to the fact that the cones have different cross-sectional areas at different heights, whereas a cylinder would still be a cylinder if you cut its height. So when you cut a cone, you get an entirely different shape than the normal cone, which is actually used in many everyday objects, such as plastic cups or construction cones. And since we can envision a truncated cone as simply a cone sliced at one of its heights, it should follow that the missing volume would be a full cone whose base is the cross-sectional area of the height you chose to slice at. So it should follow that an exact formula for the truncated cone is 1/3 base times height of the cone as if it were not truncated, minus 1/3 base times height of the empty space that is the truncation. And we can see that even if the bases and heights are different, which they are in order for a truncation to happen, that 1/3 is a common factor. So we would simplify this volume formula to 1/3 times pi, as it is a common factor in the bases, times, in parentheses, r squared times height of the truncated cone, minus r squared times height of the truncated area. And the surface area would follow the same trick. So it would be the surface area of the truncated cone minus the surface area of the empty space that constitutes the truncation. Because even though from a literal perspective it is nothing but empty space, we can use our imagination to state that if it has the same volume as the missing cone, it should therefore logically also have the same surface area, even if no surface physically exists. However, we must also pay attention to the fact that we cannot subtract the surface area of the circular base of the truncation, as it does exist on the surface of the truncated cone, in particular the topmost surface. So in conclusion, the surface area of a truncated cone would still spread out in a fan, but the radius would be different, because we remember from a full cone the radius depends on the height of the cone. And then we would add the circles that constitute the two bases. We can also perform the truncation with a slanted line instead of two parallel lines, just like the truncation of a cylinder, where the surface area would now be a more complicated trapezoid that constitutes the radius, but we would still dissect it to figure out its length, which would be the radius of the cone, and we would figure out the height, which would be the height of the cone. so we would plug those in. For volume equals 1/3 pi r squared, although we would see that we would have to multiply it by 1/2, as it would fit similar like a jigsaw piece into an identical volume to constitute a full cone. By similar reasoning, for the surface area, we would unfold this complex shape, just like we would unfold a rectangle for a full cylinder, and then we would simply add the two circles. Now that I've explained how to figure out a segment of a cone in either way, I can explain how to figure out the most complicated of the basic 3D curves, which is the sphere, using what we already know from cylinders and cones as a proof of its volume. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.